Hi class. In this lesson, we're going to be revisiting the standard library algorithms, and we're going to take a look now at how we can use the lambda expressions, which we've discussed in the last lesson, to customize the behavior of those algorithms. If you remember, we were able to use algorithms to do a bunch of useful things with containers, like sorting, searching, uh, find the max element in a vector, things like that. One of the things we were doing when we were doing that is we were always creating vectors of integers. Um, and so it is possible to create vectors of other kinds of objects, including custom objects that we've defined ourselves. In this lesson, we're going to work with a bunch of vectors of cars, basically. So we've created and worked with this car object in the past, and it's going to actually serve as a pretty good example on why we need to customize the algorithms and then how we can do that. So if you remember the car class, it has two properties. It has a VIN number and a price. Um, and I'm actually piecing together several of the things we've discussed recently, like random number generation and whatnot, so that I can actually create a create random function as well, which will just create a car with a randomly generated VIN and a randomly generated price. So there's some random stuff in here as well. But yeah, the main two elements of the car are the VIN and the price, and then we have a couple of getter functions right here, and we also have a setter function to update the price. So yeah, this is the basic car class we've been using basically all quarter. And then we've got some of the utilities that we were using earlier as well. This is a utility template function that overrides the output stream operator for a vector of objects of type T. So we're going to be able, if we have a vector of cars, for example, we're just going to be able to print out the contents of that vector in a somewhat nice format. Okay, so let's look at what we're actually doing here. So to begin with, we want to create a list of cars. Okay, so we'll create a standard vector container holding values of type car, and we'll give it a name, cars. And then we're going to create 5 cars in that list. So we're going to iterate 5 times, and on each iteration, we're going to push back what we get from calling the create random function. So we're going to create a random car, or a car with random values, and push it back to the vector. Okay. I'm just going to comment everything else out for now. Let's just look to begin with at that part of the code. So let's run it. Okay. And of course nothing happens because we didn't print anything out. So I will also add a loop somewhere. I have a place where I print out cars. Okay, here it is. So down here is a line of code that's going to print out all the cars. So let's try that one more time. I'm going to build the code, run the code, and here we go. So each time I run this program, I'm going to get a list of 5 cars, and they're going to have random VIN numbers and prices. Okay. All right, so the next thing that this code is going to do is it's going to create a special car. So what we're going to do is we're going to demonstrate find if, in fact. So we're going to try to find an object in a list. So we need to create a special object that we're going to be able to recognize, or that we're going to search for, and put it in the list. But if we always put it in the list, of course, it will always be there. So to make this slightly more interesting, I'm going to use another random number generator and maybe put the car in the list. So here's my special car. It has a special VIN number, special, and a price 1, 2, 3, 4, 5. Okay, so that's my car object. So I'm, getting a random number generator, and I'm using the Bernoulli distribution. This is for returning Boolean results, true or false, and you give the probability of returning false. So it may or may not. This variable is a Boolean, right? It may or may not decide to push the car into the back of the list. Okay, so if I just leave the code like this now, and again, let me compile and run the code, and we'll run it a few times, and you'll see that it will always create a list of 5 cars, and then it may also push that 6th car into the list, the special car into the list. Okay, so let's run this. Okay, so there's the car. There it is again. There it is again. This time it wasn't there. Okay, I think I said that it's the chance that it doesn't add it. Sorry, this is the chance of returning true. So there's a 66% chance that it will add the car into the list. Okay, so we should see that 2/3 of the time we do get the car added, and then 1/3 of the time the car is not there. All right, now for always pushing it to the back of the list, again, it's not very interesting. So to make this, again, slightly more interesting, what we're going to do is we're also going to shuffle the list. Now, shuffle happens to be another algorithm from the standard library. Shuffle takes a begin iterator and an end iterator, and it also takes a random number generator, or a random bit generator, and it will use that generator to shuffle the elements of the container. Okay, so by the time this line of code runs, we will have a list of cars. It may or may not have a special car in it, and if it does, we have no idea where in the list that car is going to be because we've shuffled the elements of that container. Okay, so let me just show you this one more time before we actually get to the finding part of the algorithm. Okay, so here you can see the special car was indeed added, and it's here at position 2. If we run it again, okay, the special car isn't there. If we run it again, still not there, still not there. Here it is, it's there, and it's at position 0. And here it is again, it's at position 1 this time. So you can see that this is pretty random, right? So we have no idea whether or not the car's in the list, and if it is, we have no idea where it is in the list. Okay. And so the reason we did all that is so that we can demonstrate the fact that we are able to find an element in a list. All right. Now, we earlier used the standard find function to find an integer by value in a list, and it would, of course, just compare every single value in the list until it saw one that was equal to the value we passed in, and if it found it, it would return the iterator, which referred to that element. In this case, though, our list contains cars. Okay. So what we need to do is we need to instruct the algorithm. We need to provide a function that the algorithm can call to ask the question, are these two objects equal? Or is this object found? Okay. So because if we don't do this, the algorithm library knows nothing about cars. It doesn't know how to compare cars. It doesn't know how to check if one car is equal to another car. Are we supposed to compare them by VIN number? Are we supposed to compare them by price? How can the standard library know about this object which we've defined ourselves? Of course it doesn't. So you will notice that the third parameter to this function is a lambda expression. Okay, the findIf function. The third parameter is a lambda expression. And that lambda expression does several things. It first captures by reference the special car that we're looking for. All right. And the reason it captures that by reference is because it's going to be invoked as the algorithm iterates through all the cars in the list, starting from the beginning and going to the end. It's going to invoke this function, and it's going to expect the function to return true if the current element it's looking at is the element we're interested in. And so our lambda expression's job is to define a function that knows how to say false all the time, except for when we're looking at the element that we're interested in, and at that point in time, it should say true. It should return true, right? Okay, so this lambda expression defines a function that's going to be invoked with a constant reference to an element in the list. Okay, so for each element in the list, it's going to invoke this function and pass that element via constant ref into this function. And what we're going to do is we're going to check that element's VIN. Okay, and if it happens to equal our special car VIN number, then we will have found the special car in the list. Okay, and again, special car is not part. It may or may not be part of the list, but we are capturing it by reference using the capture group of the lambda expression, so that we can compare the VIN of the element of the list to the VIN of the special car we know about to check whether they're equal. And I'll also uncomment the rest of this code. So if this is just a typical, it returns an iterator to the object if it's found. Otherwise, the iterator is the end iterator, so it wasn't found. So as long as the iterator is not equal to the end iterator, we did find the car. So we will print out found the car, we'll print it out, and we'll also print out the index at which it was found. Otherwise, the iterator is the end iterator, which implies that the special car we're looking for was not in the list, so we'll just print out special car was not found. So let me compile this now that I've got all the code added back. And we'll just run it a couple of times and see that it's working. Okay, so here we are. So I'm going to run main. You'll notice that the car was indeed in the list, and it was at position 0, 1, 2, 3, 4. And so the findIf function did in fact return an iterator that wasn't the end iterator. And so we entered this block of code in the if statement and printed out, found the car, okay, at index 4. So it was indeed found. If we run this again, okay, this time the car is not in the list, which you can see if you look at the list. Here the car is in the list at index 2, right? Index 0, index 5, not in the list. So you can see each time we run this code that it's either finding or not finding the car, depending on whether it's in the list. All right, so that is an example of the findIf function. And again, we would not be able to use this function to search through a list of cars. We're able to use the find function to search through a list of integers just fine, but we would not be able to use this very useful algorithm on a vector of cars unless we were able to use these lambda expressions to provide the custom behavior that instructs the function how to find the element we're looking for. All right, remember, by passing a function as a parameter, we don't really care about how this findIf function is implemented. I mean, probably it just starts at the beginning and goes to the end, right? So it's probably a pretty simple function. But yeah, we're not so interested in how it's implemented, but we are interested in customizing the part of the implementation that checks for equality, which is what we're doing with a lambda expression. Now, in this example, we're going to look at sorting. So we just did searching, now we're going to do sorting. Again, we instead of using a list of integers or a vector of integers, we now have a vector of cars. Now, a vector of integers is easy to sort because you can compare one integer to another by default and know, like, we can tell which integer is less than another integer. The less than operation is defined for integers, so it's very easy for the sort function to just do this automatically. But when you take two cars and you say, is the first car less than the second car, the sort function has no idea how to process that. Like, what does it even mean for a car to be less than another car? Are we talking about the VIN numbers? Do we want these to be ordered alphabetically by VIN number? Or maybe we're talking about the price. Or maybe there's some other property which we're interested in sorting by. So there's no way to just sort a list of cars using the default less than operator. Okay, but if we use a lambda expression, which you can see as the third parameter to this sort function, if we use a lambda expression, we can actually customize what happens when two cars are compared to each other. So the sort function, it's an algorithm, it goes through the list, it's going to look at several cars, it's going to compare several times different cars to each other, and the question it wants to answer is this car less than, or should it come before this other car? So every time it looks at two cars, it wants to know which one should come first. Okay, so if we provide a lambda expression, or if we provide this third parameter to the sort function, this is a function that will be invoked in order to answer that question. So remember, we have two cars. We want to know which one should come first. And basically, the API to this function is we'll receive those two cars as parameters, and we're supposed to return true if the first car, if the first parameter should come first in the list, and false otherwise, implying that the second parameter or the second object comes first. Okay, so here we are sorting by VIN number. So notice what I do inside of the function is I say a.vin less than b.vin. So this returns true only if the VIN number for the first parameter, the first car, is less than the VIN number for the second car. So when I run this code, let me compile and run this code. When I run this code, you'll notice that after sorting the list, the cars are in order alphabetically when we look at the VIN number. Okay, so they're completely out of order up here, but then after the list is sorted, they're in order alphabetically. And I can run this a few times. You'll see every time I run it that yes, these cars are indeed ordered alphabetically after I've sorted them. Okay, so that's really great. And the best part of it is that suppose that I'm not interested in sorting alphabetically by VIN. I want a list of cars from price, highest to lowest. It's very easy to make that change. I can say a dot price. Remember, I want to return true if the first element should come first. So I want to basically look at the price and see which one is higher. So if the price of car A is greater than the price of car B, I'll return true. Okay. So return a dot price greater than b dot price. What this will do, and let me compile again, what this will do is it will now sort the list by price from greatest to least. So notice how I'm able to change the implementation of the lambda expression. Let's go ahead and, let's go ahead and run the program. There we go, sorted in order by price from highest to lowest. So by changing the implementation of my lambda expression, I'm able to change how the sort algorithm works. I'm not changing the algorithm itself, the algorithm reaches a point where it needs to ask a specific question, and I'm able to customize how that question is answered. When it comes to finding the question we're trying to answer is this element the one I'm looking for? When it comes to sorting, the question I'm trying to answer is, given these two elements, which one comes first? So by changing the implementation of this lambda expression function body, we're able to change the answer to that question and change how the objects are sorted. So it's actually very powerful to be able to do this, to be able to customize sorting by using these lambda expressions. Now, one other thing I want to point out here is that a lambda expression is basically always interchangeable with a regular function. So what does this expression do? Okay, let me just cut it out here and paste it up here. We're just going to convert it to a free function. So I'm going to call it compare. It's going to, again, take two parameters and return true if the price of the first is bigger than the price of the second. And so it does return a bool. Okay, so here's just a regular free function called compare. Okay, and instead of having a lambda here, I'm just going to send that function. So functions can be parameters to other functions. And lambda expressions are basically just functions, okay, which is why they can also be parameters to other functions. So if I run this code, I'm going to compile it one more time and run it. You're going to see that it's exactly the same. Nothing has changed. It still compares cars in order by price from greatest to least. Okay, so everything is still working as it did before. So passing a function is no different than passing a lambda expression. All right, they're interchangeable. So now the question you should be asking is, well, why do I want to use a lambda expression? Why not just define a function? And the basic answer to that question is a function, when you put it, at the global scope of your code, it's something that can be reused all over the code base. So, this is just a small example, but you can imagine several classes or other parts of even this class, multiple places where we might invoke the compare function and use it. Okay. But this function is very specific. What it does is it compares cars by price. Okay. And maybe it's not something that's really reusable. Maybe we only really need it once. Okay, so if you have a function that needs to be that provides a general utility that can be used all over your program, that's when you should make it a free function, define it somewhere in your code base that other code can access and use it. If you need the behavior of a function, but it's just like a one-off thing, it only really applies to this very specific circumstance, that's when you're going to want to use a lambda expression. So let me switch back to the lambda expression code. Here it is. This behavior, this function which sorts cars by price from greatest to least, this is very specific to what I'm looking for in this one part of my code. So typically when you need something, like a one-off thing that's very specific and it's not a kind of function you're going to be calling multiple times from different parts of your code, that's when it makes sense to use a lambda expression. And lambda expressions are very concise. They basically just look like a function, which is nice. And they're expressive. Once you get used, I know the syntax is a little weird, but once you get used to it, they're very readable. I can look at this code and say, okay, I'm sorting my cars, starting at the beginning, going to the end. I'm sorting the whole container of cars. And how am I comparing those cars? Oh, I'm comparing by price. Okay, so it does end up being fairly readable. Now in this next example, let's let's revisit something we looked at before with the list of integers. We were finding the max element and the min element. Okay, um, so if we have a list of cars, and we want to find the min element, again, what is the minimum car? When you have a generic car, how do you know what the minimum is? It doesn't really make sense. Okay, it makes sense to say which integer is the smallest in a list, but it really doesn't make sense to say which car is the smallest in a list. But if you're looking for something specific, like which is the cheapest car in the list, so which car has the lowest price, that's a question that makes sense to ask. So in this example, we are calling the min element function, which again returns the minimum element of a list. And just like the sort function, it needs to compare two elements from that list to each other and say, hey, is this one greater or is this one smaller than the other one? So this function is supposed to return true if element A is less than, in the context of finding the minimum, is less than element B. So if we're looking for which car is the cheapest, which car has the lowest price, we just simply implement this function so that it checks the price. So here's my lambda expression right here. We take A and B, two different parameters, two different elements from the list, and we just return true if A price is less than B price. Okay, so by customizing the algorithm in this way, it will return iterator referring to the car with the lowest price. Okay, so if you look at this example, we create the list of cars, we print it out, we find the min element, which again returns an iterator, and then if that iterator is not the end iterator, it means we found something inside of the list, we'll just dereference it and print it out. So let me go ahead and compile and run this code. Okay, great. So here's my list of cars, and if we try to look, without looking down here, if we look through the list, we'll notice that the smallest price is this 6,488 right here. And indeed, the cheapest car is that car which had that price. Okay, and if I run this again or a couple more times, you'll see that each time it is indeed finding 7,900. This happens to be the smallest element in this list. So it is finding the minimum priced car in the list. If instead we want to say, hey, what's the min element in terms of alphabetical order, we could instead compare VIN numbers, right? So if we want to say, okay, which car is alphabetically first? I know for real VIN numbers that doesn't really make sense, but for the sake of example, let's see which VIN value is alphabetically first. So let's go ahead and do this. And here we have the one that starts with B. Okay. If we look at this list, it's the one that starts with D. So that's alphabetically first in the list. All right, this one happens to be the F, which is here. And this one happens to be the E, which is right here. All right, so we're able, again, as you can see, to customize what this algorithm is actually looking for by providing a lambda expression. So this is really a powerful technique. There's dozens upon dozens of algorithms in the standard library. We're obviously not talking about all of them. A couple of them which I find to be really, really useful is any of and all of. The any of algorithm returns true if any of the elements in the list satisfy a condition. Okay, and the condition we can provide in a lambda expression, which will take a reference to that element, and only needs to return true if it does satisfy the condition. So here we're checking if the VIN number of the first letter of the VIN number is equivalent to the character A. So basically this any of algorithm right here will return true if any of the cars in the list start with a letter A in the VIN number. Okay, so I've named the result any car has VIN with A. This is a Boolean result. All right. The all of algorithm will return true if all of the elements in the list match the condition. In this case, the condition is the price being greater than 8,000. So if we print out a list of cars and every single car in the list has a price greater than 8,000, this condition will be true. All right. So let's go ahead and run this and just see what happens. Again, we're going to have randomly generated lists, so each time we run it, we're probably going to get something a little bit different. All right, so let's run it. So here's our list. Do any of the cars start with A? No. And you can see none of them start with A. Do all the cars cost more than 8,000? No. So there must be a car in here. Here it is that costs less than 8,000. Let's try again. In this case, we did get a yes here, so there is an element of the list which starts with A. Here it is. And no, not all of them were greater than 8,000. We had a couple this time that were less than 8,000. Let's run it a couple more times and see if we can get a yes to the second question. Here we go. Do all the cars cost more than 8,000? This time we got a yes. And if you look at the prices, they are all above 8,000. So when you have a list of data, I find myself using these algorithms all the time. You often want to answer these kinds of questions. Do any of the elements match a criteria, or do all of the elements match a certain criteria? Okay, now the last example I want to go over on the topic of customizing algorithms for the standard library is transform. Transform is an algorithm you can use when you have a list of something and you want to change it to a list of something else. For example, we have a list of cars, right? But suppose we just want a list of the VIN numbers. So can we extract all the VIN numbers from those cars and have just a list of those VIN numbers? So what we do in this example, again, the first part is exactly the same as it always is. We're going to create a list of 5 random cars. We're going to print it out. Great. I'm also going to make a vector of strings for the VINs. Right now it's empty, it doesn't have anything in it, but I'm going to use the transform function, which will iterate from the beginning to the end of the cars list. The third parameter is kind of interesting. It's back inserter to VINs. Basically, this is supposed to be an iterator that allows you to insert into another container. So this is going to be used. You can look it up more details online. If I take a back inserter to a container, it's going to, each time it goes through this list of cars for each element, it's going to insert the thing that I generate into the back of this other list. So what do I generate? Well, for every element in the list, which is a car, I'm going to return car.vin. So this algorithm, this transform algorithm, is going to go through all the elements of my list. And for each element, it's going to transform it into the thing I return from the body of this lambda expression or this function, which happens to be just the VIN number. So if I construct this like this, where my lambda expression just returns the VIN number from each car, I'm essentially taking a car and converting it to a string, right? The string being the actual VIN number. And by using the back inserter into the VINs container, I'm going to end up, by the time I'm done, with VINs being full of all the VIN numbers of the cars. Finally, I'm going to sort the VIN numbers. Since they're strings, the sort algorithm already knows how to handle strings, so I don't have to customize it with a lambda expression. Yeah, so then I'm going to print out the sorted VINs. So let's just go ahead and run it and see what it looks like. That might help us understand a little bit better what's going on. Okay, so here's my list of cars. Okay, and what I come out with on the other end is a list of VINs in sorted order. So you'll notice these are in alphabetical order. Again, these are all the VIN numbers. These will all match the VIN numbers from my original list. Okay, but they're sorted. Let's run it one more time. You can see one more time. Here's a bunch of random cars, and here's just the VIN numbers sorted. Okay, so you can imagine how this might be useful as well, right? And you can do things that are much more complicated than just returning a property of an object. You can actually, make modifications. Perhaps we want to look at the price, and we want to divide all the prices by 2 for some reason. So we can return the price divided by 2, or maybe we're doing a sale, and so we'd want to see what all the prices would be if we multiplied by 10% or something like that. So you can do all kinds of interesting things in this transform function, but what's actually going on is just this: every element in the container this function will be called on that element, and you perform the transformation that you want and return some new data type, something else that you're interested in transforming into, in this case strings. Okay, so if I have a vector of string for VINs, I can then insert everything I'm returning from this transformation into that other container. And then when I'm done, I have a list of just the VINs, as we saw. So that's the last example we're going to do for this specific topic. I know there were a lot of examples, but hopefully you can sort of start to get the picture that this is really useful stuff. And the standard library is designed to provide a lot of the general purpose functionality that you would need for a lot of the programming you might do. And now that we've learned about containers, we've learned about iterators, we've learned about algorithms, and we've learned about how we can customize the behavior of those algorithms using Lambda expressions. um, Hopefully you're starting to get the sense that this is actually a lot of really powerful stuff, and it covers a lot of the programming that you might need to do. A lot of the questions you might need to answer uh, can usually be answered by just using components that are provided in the standard library. So I encourage you to go out and learn more about the standard library. Like I said, there's like something like 120 or so algorithms that are available that all do different things. We only talked about a few of the containers, but there's several different containers that can be used. So there's really a lot to learn in the standard library.